this video gives you a review that covers simulation. In class, we talk about two applications for simulation. One is to simulate stock prices and return. Another one is to apply Monte Carlo simulation to investment problems. The model that we use to simulate stock prices are here. So on the left-hand side, this is the log return, which is defined by here. So we are taking the log of the price ratio. On the right-hand side, we'll generate some random returns based on these. Delta T is our time interval. It can be at monthly frequency, then it will be 1 divided by 12. If it's at weekly frequency, then it's 1 divided by 52. Daily, so 1 divided by 252 trading days. And sigma here is the volatility of the stock returns. Here, this view is the average return for the stocks. And Z will be the standard normal deviate, which is generated by this Excel function. It's going to be some random numbers that follows normal distribution. And the randomness of the return is all coming from this Z. Now, if we have this return generated by this function, then we can basically replace return by this log, ST divided by ST minus 1. Put it to the left-hand side, do some rearrangement. We can have stock prices simulated by the function on the right-hand side here. Now, it does depend on your value that you gain from the previous steps for ST minus 1. So assuming that if you know S0, which is the current price, then all your following price will be generated by some random process, and ST, your stock price in time T, will be depending on the stock price, which is contains some randomness in time T minus 1, and times a new random variable, a new random numbers, which is generated by this process. So to use a graph to simply illustrate that, so the mu here simply represents the drift that you have, the average level of this return, and the sigma adds the shock to the price movement or the return movement. So here will be the zig and zag. The magnitude of this shock is determined by this sigma. Now let's look at the questions. For question 9, you'll need to simulate stock returns and calculate portfolio statistics. This stock return A and stock return B, we can have the mu 15% and sigma 30% for A, 8% for B, 15% for B for the sigma. And they have correlation here. So what we need to do here is to simulate stock returns that are correlated. And then construct a portfolio composed of 60% A and 40% B. You're going to hold it for 2 years and simulate it 20 more returns, given the parameters showed up here. Now first enter the value for average return, 15%, 30%, 8%, and 15%. Correlation, 0.3. Delta T is our frequency for the return is monthly. Proportion for A will be 60. Portfolio return, simply follow the formula here for a portfolio of 2 assets. For simulating returns, we should first get Z1 and Z2, and they are correlated. So the way of doing that is to first generate Z1 that follows an independent normal distribution, and then generate Z2 that depends on Z1 in a way that Z1 and Z2 their correlation equals to 0.3. So we need this transformation of Z1 and also adding another distribution that's independent from Z1 here. So that Z2 here has its own random performance. Return will be following this process. So we will adjust the numbers, these random numbers that follows normal distribution, adjust it such that it can have a mean equals to this mu and has a standard deviation that equals to this sigma. And then calculate the mean of stock A and stock B, average, which should be the sample mean of simulated returns that we have. Okay, so just to double check, the correlation of the return here should be the same as the correlation for Z. Going further, we want to compute portfolio simulated return and standard deviation. So simulated monthly return here will be following the calculation here. And this is actually related to question B already. So I'm gonna go ahead and copy the formula here. So here for these two numbers, we basically want to generate annualized return. So here, the monthly return in monthly frequency, sigma is for the volatility of monthly return. If we want to calculate the annual return and annual portfolio sigma, these are the simple transformation. And further, we want to run multiple simulations, different experiments. So one thing that we can do is to utilize the data table equals to return equals to sigma. Column input for just generating more simulation will be just any blank cell. Fresh. I want to compare our simulated return with the true return and the true sigma equals average the max is the maximum of portfolio return based on our simulation. Mean will be the minimum. So among 20 different experiments, the maximum simulated return for the portfolio return will be 50%. Minimum is negative 20%, so there's still a lot of volatility out there. And for sigma, so 26 for the max, 12% sigma, portfolio sigma for the mean, minimum. So on average, our estimates are pretty close here. Our simulated returns are pretty close to the actual return. So you can compare here, the simulated and anticipated portfolio return. Is your estimation good enough? So just looking at the difference of these two, I think my calculation here shows a pretty nice convergence to the true value of this anticipated portfolio return and sigma. Now going forward to the next question, simulate 36 monthly return for multiple correlated stocks, report a sample mean of return. Now, what we learned in class is to just simulate two different stocks that are correlated. So two different stock returns, these two returns are correlated and the correlation is 0.3. But one thing that we have not talked about in class is how to basically simulate much more returns for a lot of different stocks. And these a lot of different stocks, they are all correlated. So it actually can be done very easily with just some simple steps. Now I'm going to demonstrate it here. Now let's look at how to do that. So basically we're going to utilize a decomposition of variance covariance matrix, which is called L. So we first need to define S, which is the variance covariance matrix. So we'll have variance here in this diagonal element and all other elements variance. And we'll utilize L matrix such that L times L transpose equals to S. And we need to create different standard normal random numbers. So just use our normal way of creating these random numbers. The return will be following this formula, this process. So we'll adjust the random numbers by the L matrix and also adding the mu, the drift, to the process. Now we're going to replicate or repeat the process of generating 1R so that we can have multiple simulations. You don't need to manually calculate it. So everything will be processed in the VBA code. So we actually here define the VBA code called correlated normal. So we'll first, this correlated normal will actually calculate what you have here, what we were demonstrating here. So what you can do is first copy the code here and calculate return. Equals plus correlated normal, letting the variance covariance matrix enter. And you can see that it has one more line here, which is equals to the anticipated future mean. So we want to get rid of this line, this redundant row. So probably what we can do is to further modify our VBA code. So what's happening here is I think there's no issue here for this calculation. It's just trying to calculate the multiplication of the L matrix and also the random numbers. So nothing wrong here. Then we can further check, do we have one more row or one more column by here? So here it generates the random numbers. So we're going to check equals to U random list for the variance covariance matrix. And you're going to see that it's a redundant column. So I would need to modify the code. So basically I will delete here, delete the the one extra column. Okay, it turns out to be only one series of random number, and that's great. This is in column, so what we need to do, just to make the simple, you can do it, make it into one row by changing everything here, but I just want to simplify everything. So the easiest that I can think of is just to transpose the numbers here. Okay, and enter, and now it becomes just one row. So I'll then fix the parameters for mu and fix variance covariance matrix. Enter, drag it down. And we're done. And finally, calculating the average mean for the simulated return. We have only 36 trials, so 36 simulated returns. So this returns here can be a little bit different from the anticipated value. Finally, going to the last questions. This is related to an application of this is related to Marcus' investment plan. So Marcus is 25 years old. He has a new job, intends to save 10,000 today, and in each of the next 34 years. So each of the next 34 years, he's going to deposit $10,000. And he has decided on an investment policy in which he invests 30% in risk-free and 3% with this 3% interest rate, and 70% in market portfolio that has a log return equals to 7% and standard deviation equals to 14%. Now we want to show that Marcus' accumulation by the time he is 60 years old. This will be just one experiment for the simulation. And then if we want to create more simulation, we're going to generate data table. So our data table will run the simulation for 100 times in order to determine the appropriate probability of achieving the goal. The goal is Marcus wants to have $1 million by the time he hits 60. So before he retired, you want to accumulate $1 million with his savings and also with his investment plan. So he wants to see how possible that he can achieve this. And then second is to determine the relation between the proportion invested in the risky assets and the probability of achieving the goal at 60. So we're going to vary the proportion that Marcus will invest into the risky assets. So here currently, the assumption here, the proportion invested into market portfolio will be 1 minus 30%, which is 70%. So we're going to vary this proportion of his portfolio and change that proportion from 0 all the way to 100% and make the advice regarding some changes that Marcus can make for his investment plan. So first, the goal here is $1 million. So, which is here. And the accumulation at age 60 will be whatever that he had at the age of 60 here. And the investment plan can be set up in this way. So his new investment every year will be equals to $10,000 deposit or $10,000 savings to his investment account. The end of the period equals to the sum of these two. So this will be the balance in Marcus' account times 1 plus portfolio return. The idea is here, we just need to get what is 1 plus return here. Now our return here, they are measured by the log return. So these are log returns. So we need to take EXP of the log return. And then we can do this first for the part that relates to bonds. So it's going to be 1 minus 70%. So invest 30% in bond times EXP 3. So next we need to add the proportion that can attribute it to market portfolio. So it's going to be the balance times the proportion, 70%, times the return, which is drift, mean, plus sigma times random numbers. So I have one parenthesis here, one parenthesis here. Yeah, I need one more parenthesis. Yes. Okay, good. So next year, the balance will be whatever he has here, the balance at the end of last year. Just drag all the way down. So now I can look at the next question. So we set up everything here. For this round of simulation, Marcus actually have the chance of getting accumulated more than $1 million. So we just need to run a couple more simulations to see what's the likelihood that he can achieve the goal. So we will need to run 1,100 different simulations. For each simulation, you can basically calculate the probability that Marcus achieved the goal with accumulation of more than $1 million. And we will also need to have some row input for this data table. We're going to change the proportion for this investment plan to be invested into the market portfolio. So currently it's 70%, which is here. And we will change this, reduce the percentage invested into the equity, or increase the percentage invested into the equity to see how the probability of achieving the goal will change according to this asset allocation. So first, the table header would be the accumulation at 60, because we want Excel to populate it. And then select all of these, the whole data table. Data, what if analysis, data table. Column input is nothing. Row input, however, should be the percentage in risky asset. So the percentage initially is 70% for calculating the number here for the table header. Okay, and you probably need to refresh it. So press F9. Okay, it took some while for my laptop to run the simulation, and now everything is refreshed. So here, when your proportion, your asset allocation to risky asset is 0, so these should all be the same, meaning that because you don't have randomness from the risky investment. So this will be purely coming from the bond, from the risk-free rate. So it's going to fix for all the experiment. But once you have some proportion investing into risky assets, so which will be affected by the random numbers generated by this part, by this Z, you will have different values for different experiment. Now we want to see the probability of achieving the goal. The goal will be $1 million. So we will need to count the number of times that we have the numbers down here, simulated numbers for the final accumulation of savings. So use COUNTIF function to see how many times the arrays going down that is greater than divided by the number of experiments that we have. So 0% here, bracket. I need to fix the goal. And next, with this probability that calculated for achieving the goal, I think the next step will be for you to discuss what kind of advice that you can give for Marcus, since you already have this estimation. So how can he adjust, whether he needs to adjust his investment plan. So that will be a discussion that you can have. I think the picture is pretty clear here. So you can talk about here the proportion investing to the market portfolio, and according to this chance of achieving the goal, which proportion that Marcus can choose, which is a good range that he can choose to invest, allocate his assets.